Have you ever wondered just how much waste goes into our cup of coffee? The plastic cup and straw is a given, but what about the coffee itself? Making coffee is a very rigorous process, and it produces quite a lot of waste, most especially coffee grounds. Now, these grounds are given out by a lot of coffee shops for good reason. They're byproducts, waste materials, and they have a lot of uses too, most notably for gardening and skincare. However, coffee grounds also contain adsorptive properties, which means certain components adhere to its surface, like the heavy metals lead, mercury, and such. With this, our study explores the use of coffee grounds as a means to remove textile dyes from water. Textile dyes are among the biggest contributors of pollution in bodies of water around the world, mostly because of the textile printing and clothing industries. And that goes to show just how much we have to find ways to remove them.
Here, we'd like to introduce our WCG-derived bioelastomeric foam, which is made up mostly by an acetoxy polydimethylsiloxane elastomer base and the waste coffee grounds itself. Typically, waste coffee grounds are used in adsorption studies in its powdered form. However, this form makes it hard to extract the grounds post-adsorption. In this compact form, extraction is made a lot easier. This is what the foam looks like to the naked eye. And with the SEM image, we can see that the coffee grounds are held together by the elastomeric base. FTIR spectra analysis also showed that the interaction between the elastomer and the grounds are physical, which means the elastomeric base is only acting as a scaffold for the grounds. In order to test the adsorption capacity of the foam, certain parameters, specifically initial concentration of the dye solutions, contact time, and adsorbent dosage, were checked to see if these parameters affected the amount of dye that could be removed by the foam. The dyes used were methyl violet and methylene blue, two common dyes that have slight adverse effects on humans and/or animals, and the foams used for all tests were standardized to have the same approximate dimensions and weight.
As seen on this chart, there is no significant change in the adsorption capacity of the foam when the initial concentration of the dyes are adjusted. Meanwhile, adsorption capacity has been observed to increase along with contact time and adsorbent dosage, which shows that longer exposure to the dyes paired with higher amounts of the foam increases the amount of dye that is extracted from the solution. However, after a certain point, redundancy can be observed with adsorbent dosage, which is between 2 and 3 pieces of foam. This means equilibrium may have been attained after 24 hours with just 2 pieces of foam, which explains the small difference between the removal efficiency of the two parameters. The foam's peak adsorption capacity in all of the tests were attained with 3 pieces of foam submerged in the dye solution for 24 hours. The removal efficiencies are 91% for methyl violet and 97% for methylene blue with these parameters. With this, we can see that the foam is highly effective in removing both of the organic dyes used in this study, even in a still solution setup. One downside, however, is that the foam takes slightly longer to reach equilibrium during the adsorption process. Compared to the original powdered form of the coffee grounds, the foam has a smaller surface area, which means there are less active sorption sites exposed to the dye solution. Despite this issue, the foam is able to retain its compact structure after being used, so extracting it from the solution is easier compared to filtering powdered coffee grounds, which is its greatest advantage. And that concludes our presentation. Thank you very much.